This scheme is a reminder that the final measured concentration in the cuvette, which is the same as the concentration here in this test tube, because we simply transferred some of what was in the test tube into the cuvette, and that didn't involve any kind of diluting. This concentration is not the same as the concentration of the original sample that we're trying to quantify. Since we know the final concentration of this dilution, and we know both volumes, the volume we transferred into this test tube and the volume we diluted the test tube to, we can solve for the concentration of the iron in the preceding flask. We can do the same to back calculate to the original concentration of iron in our beaker. The underlying assumption is that 100% of the iron in our serial sample was collected on our magnet and solubilized and then complexed with the thiocyanate to give it its reddish color so it could be detected. Of course, those are key assumptions. Our job is to work backwards now, from the absorbance in our cuvette to the amount of iron in our beaker.
So, for this next and final video, we're going to determine the first back calculation. So the code above here determines how much arsenic is found in the cuvette, or the concentration of the arsenic in the cuvette. Using this, however, we can then take this value and use an M1V1 M2V2 equation and back calculate it to get the value before we diluted the arsenic. And so to do so, we're taking, let's input these values that we have. And so the first value that we have is this arsenic concentration that we got. Yours will be iron, but ours is 0.000530. So that's the last concentration that we have, or the M2 value. So let's put that in. Then we know that the volume is 10 milliliters. 10, right? And finally, we took 5 milliliters from the original flask, which was eventually diluted. So now we have three values of the M1V1 M2V2 equation. Now, using some algebra, we can calculate, or we can isolate the M1 value because we have V1, M2, and V2. And if we can get the M1 value, we can get the concentration before we diluted it. So we name these pretty conveniently. M1V1 equals M2V2. Another way to look at it is as each of these values are variables. So we can say the M2 cuvette is also known as M2, right? And the V2 cuvette is also known as V2. And the V1 flask is known as V1. So if we just think of these as the variable values, we know that M1V1 times V1 is equal to M2 times V2, right? And so if we were to solve this for M1, that would be the value that we would put here. Now, if we were to do this algebraically, we have to solve for M1, right? That's the M1 flask that we're looking for. So I think we can just divide both sides by V1, and we get the final equation of M1 is equal to M2 times V2 divided by V1, right? So now we have, this is the equation that we want, but that's not the right names. Those are just like placeholders that we were using to make it easier to think about. So using the right names, let's substitute these correct names in. So M1 is also known as the M1 flask. So we can write this as M1 flask. And we know that M2 is also known as M2 cuvette. I'm going to put parentheses here just so it's really obvious of what the order of operations are. And then V2, or V2, which we would normally have here, is also known as V2 cuvette. And all of that is divided by V1, which we can also call V1 flask. So then we can get rid of the work that we did. And now this is the correct value, let's put it in the right spot, that this back calculation performs. So then, this is the concentration that was before the first test tube dilution.